Transcription initiation is arguably the most complex and highly regulated step of transcription. It requires an orchestra of cis and trans regulatory elements to articulate and direct transcriptional machinery. Proximal promoter elements are stretches of DNA sequence directly upstream from the start site of the gene to which transcription factors, including RNA polymerase, binds. Distal promoter elements are sequences of DNA up to thousands of kilobases away from the start site, where other transcription factors bind. Transcription initiation is an eloquent process, and for the appropriate initiation, proximal and distal promoter elements must associate, and that is the role of the mediator complex. The mediator complex is a multi-protein complex that functions as a transcriptional coactivator. That is, a protein complex which binds activators to increase the rate of transcription of a gene. In yeast, the MED15 subunit of the mediator complex binds a multitude of transcriptional activators, including Gal4 and GCN4, through its activation binding domain. Gal4 contains a DNA binding domain, a central regulatory domain, and a C-terminal activation domain. Gal4 is an acidic transcription activator and contains an abundance of acidic residues which embed hydrophobic stretches in its activation domain. This primary sequence architecture gives rise to intrinsic disorder in this region when it is not bound to its binding partner, an activation binding domain. Gal4's activation domain transitions from being intrinsically disordered in its unbound state and adopts an alpha helical structure upon binding one of the 4 MED15 activation binding domains in the mediator complex. MED15's activation binding domain 1 contains a shallow hydrophobic groove that serves as the activation binding site, whereas activation binding domain 2 has binding distributed over its surface. Owing to Gal4 binding structurally diverse activation binding domains on MED15 indicates Gal4 binding in one orientation to all activation binding domains is unlikely. Due to Gal4 not being limited to binding activation binding domains in a single orientation, points towards a fuzzy binding interface. Fuzzy interactions cannot be described by a single orientation between binding partners and also enables activation domains to bind a greater number of binding partners. The low affinity of MED15's activation binding domains to Gal4 further facilitates fuzzy binding, as a singular high affinity binding site would have more stringent conformational constraints. GCN4 is another yeast transcriptional activator which also binds MED15 via a fuzzy complex. The primary amino acid sequence of Gal4 and GCN4 is highly diverse, indicating the binding to MED15 is a sequence-independent interaction. MED15 activation binding domains are more conformationally constrained than their binding partners Gal4 or GCN4. The structure imposed by the activation binding domains does not restrict binding partners to one conformation, however. The binding surfaces have low sequence specificity, hence enabling diverse partners to bind the same sites. The low sequence specificity is also amplified in the fact that the binding sites are large and open, meaning one orientation of the binding partner is not necessary. These things assist MED15 binding different binding partners using a fuzzy interface. This interaction is not reliant on sidechain to sidechain interactions, but instead a hydrophobic cloud, which permits more flexibility of the activation domain that is binding. As seen in this hydrophobicity plot of Gal4 binding activation binding domain 1, where the hydrophobic residues are highlighted in red. The fuzzy binding interface is highly hydrophobic, and hence, as long as the binding partner contains an abundance of hydrophobic residues, this binding will be energetically favourable despite the low structural constraints needed. The property of fuzzy binding can explain how one activator binds multiple unrelated targets, and thus the mediator can function as a coactivator to regulate gene expression for more than one unrelated gene. This knowledge will also assist future determination of the way in which activation domains bind their partners, and hence enable us to probe these interactions more accurately. Studies to precisely define the minimal activator motif, as well as examining the mechanism of more complex activators, will be highly informative for defining different classes of activators. This will give us a better understanding of the diverse mechanisms used in eukaryotic transcriptional regulation.